This is Deuk. He says his name is not pronounced Hyo, like you might spell her, right? But through circumstances, it is now spelled Hyo. Anyway, he's a research professor at Georgia Tech and a faculty candidate here, and he'll tell us about his work on wireless, RF for wireless.
Thank you, Roy. My name is Deuk Hyoun. My last name is Heo, but I misspelled my name when I take a GRE. And at that time, I didn't know, exact pronunciation of English name, so I use HEO. So whenever people say your name is Heo, I found that I made big mistake. But I need to use this one because I use this name for my paper and everything. So right now I can change my name. So you can call me Deuk. Yeah, I came from Georgia Tech, and this is the pitch that is sort of symbol of Georgia. And I'm working with Dr. Joy Laska. He is a research director of the Yamakura Initiative of the Georgia Tech. The title I'd like to present is Advanced Technologies for Highly Integrated RFIC Module for Future Wireless Communications. To just break ice, this is Georgia Tech. This is the main building. From the electrical engineering building, we took a picture, and this is the downtown area. And in the downtown, Georgia Tech is located in there. And this is the architecture engineering, and this is the building of this one. There's some interesting in Atlanta. There are Masters golf tournament every year, and Coca-Cola headquarters, and then Delta, and CNN, and also I like Atlanta Braves. Have you heard about that?
We hate these Atlanta Braves. At least I do.
Okay, this is the presentation of outline and introductions, and there are two different kind of prototype demonstrations. One is a compact silicon-based power amplifier, focusing on the passive on chip and passive on package solutions, and also prototype solution. I'm gonna demonstrate CMOS and silicon germanium HPT DACT and home RF power amplifier module. And for the second, I'll show just compact gas-based RF front-end module. This is based on the 3D integrated embedded passive implementation. The prototype can be a 802.11a wireless LAN RF front-end module. I have some specialty in the device modeling also, and also the other area is some background converter receiver. But here I'm gonna just show you just two category of the work, And also I'd like to conclude my talk with the future work. There are a lot of research activities in the wireless application area. As you can see, the mobility and then data rates is related to the inverse wise. So whenever you're gonna have more mobility, you lose the data rate, and then vice versa. Whenever you achieve more higher data rate, you cannot achieve the high mobility. So my main focus area currently is 802.11a and b. The research direction is moving toward to achieving more high mobility and then high data rate. So that is, we can say, next generation wireless communications, RF front-end. Today's talk is focused on those two, wireless LAN topics. To implement those kind of RF front-end, RF transceivers, there are two different kind of approaches. You can say system-on-chip solutions for the RF, and the other solution can be a system-on-package solutions. Today, I'm going to category two different kind of topic. One is system-on-chip solutions for RF. The advantage of system-on-chip solutions, as you can see, local solutions is possible based on the silicon technology, because most of the digital logic can be implemented in the silicon technology, and also based on higher integrations, we can achieve a small size. Finally, we can get local solutions, and also implementing some kind of additional features on the silicon RF transceiver. We can get smart RF. Smart RF means, including some kind of additional features such as power control or, some kind of, protection circuit. We can achieve, we can include some kind of intelligence on the silicon level design. So we can call it system smart RF. In contrast, those kind of issues, we have some disadvantage of the, system-on-chip solutions. There are a lot of, passive losses on the silicon due to, lossless silicon substrate. So, and also there are other interference between the lossless silicon substrate. There are coupling between the, digital circuit and analog circuit. You need to be careful to decouple those kind of interference. Especially we need a robust, substrate contact, and then making to the, ground connection very. You need to good, ground connections, and also to implement the on-chip solutions, it may take a longer, the longer design cycle. Especially of RF front end and then analog end, it's really hard to achieve, one-time success. So that's the reason why we need a lot of good model. And we need a lot of sensitive analysis and also yield analysis. Those kind of all different kind of analysis is very important, especially for the RF and analog circuit design. And next, the system on package. What is system on package solutions? This is just provide a single package solution by integrating embedded passive and RFIC using state of the art of packaging technology. This kind of technology, we can implement discrete components to the embedded one, and also we can add functionality in the package, such as filter and then balun, and also antennas solutions. Anyway, it's really hard to implement antenna on the system on chip, isn't it? It totally depends on your frequency range. Let's assume you are developing some kind of 60 gigahertz millimeter wave, RF front end, and then you may be possible to implement antenna on system-on-chip solutions because the frequency is very larger and larger, higher and higher. So your size of the antenna is smaller and smaller. You can make some kind of small size of antenna based on some MEMS or wafer level packaging solutions. But lower frequency, let's assume below 6 gigahertz, is not possible to implement those kind of on-chip antenna. Nobody wanna do that. So anyway, you need to separate antenna, and you need to separate some kind of surface acoustic filter or the other high Q filters or some balun. Balun is have you heard of the balun? Balun is unbalanced and balanced, single-ended to balanced signal transformer. So this kind of transformer, we can build some kind of you can overcome some kind of issue on silicon technology design, such as breakdown issues. You split design, and then power level is lower down half of that, and then that means your breakdown maybe can be overcome. So that kind of circuit can be implemented in the on package, and also you can realize high Q embedded passive such as the high Q inductors. That's pretty critical to get good phase noise for the oscillator and good efficiency for the power amplifier. If you are losing some loss on the bias feeding path of the power amplifier, it's very sensitive, those kind of losses, to achieve a high efficiency power amplifier. If you are developing some kind of mobile solutions, mobile terminal, the power efficiency is pretty critical issues. If your PA almost consumes of 1/3 of the power or half of the power, so your PA's power efficiency is critical. So if you can implement some high Q inductors, it saves your efficiency. So in this point of view, there are two different kind of approaches: system on chip and system on package solutions. Here are some simple block diagram for the RF transceiver. There are some baseband design and IF and analog interface design, and also mixer and VCO, and then gain amplifier and power amplifier, filter and duplexer. Duplex is this sort of can be filters with different kind of bandwidth, And then receiving part is here, low noise amplifier and down converter, and IF and analog design. System on chip solutions can be cover this part or cover this part. If you have a good isolation between those RF front end and then baseband design, system on chip solution can cover this area. But PA, if you are really focusing on the silicon PA, maybe you need to separate solutions can be possible also, because silicon PA still there are a lot of issues to achieve 0 dBm power amplifier. 0 dBm means 1 milliwatt, okay, and 27 or 20 dBm power amplifier is still possible solutions. That means it's okay. But if you are developing some kind of half watt PA, it's really hard to achieve with a reasonable number of linearity, reasonable number of efficiency. So we can consider we can incorporate this one into the on chip or off chip. Totally depends on the spec. This is the other way is system on package. This can stretch up to here or here. Totally depends on the applications. Implementing this one system on chip or incorporating everything, the other parts, antenna and filter and duplexer can implement it on the chip, on the package. So we can combine those two solutions, on the same package, because package can give us good high Q performance, filter and then antenna solutions. So this is the one of the solutions to achieve high-end RF transceiver. There are some technical mapping here. Those whole thing can be implemented on package, and this can be implemented on the on-chip. All the baseband amplifier, IF and RF analog, and also low noise amplifier and driving amplifier, mixer, switch can be implemented in the on-chip cases. But there are some issues of VCO and the PA cases. Especially for VCO, there are phase noise issues. So if you have a good, high Q, resonator, you can achieve, good high-end, VCO. But on-chip silicon has a lot of loss, so your Q is not that high. Let's assume you're gonna say 5 or 10, below 10, Q factors. So it's really hard to achieve, high Q passive and also resulting in, poor phase noise performance. So in that point of view, this is totally depends on the applications. Your application is targeting for low end RF transceiver. It's okay to implement on chip. If you are targeting more higher, you need to come up with different technology instead of silicon or GaAs or some packaging solutions. PA case is same story. PA case is also 20 dBm is okay, 24 dBm is okay to implement, based on the silicon technology. But you are targeting more than that. You need to come up with, different technology, switching amplifier, incorporating a lot of, transformer. But still, if you are targeting linear PA, it's really hard to achieve with a good, reasonable number of, efficiency. If you are targeting high efficiency PA, it's okay. You can possibly build 1 watt PA based on the silicon technology. So PA and VCO is on the boundary, and then the other power combiner and balun, and then filter and antenna and duplexer and high Q inductor and capacitors can be implemented on the package. So this criteria can cover maybe half of that. Depends on the technology. So nowadays, CMOS RF process also available from the TSMC foundry. So maybe if we access that kind of technology, we may achieve, half of the circuit here. But still, there are some issues, antenna and duplexer. This is 3D RF front end, module example. As you can see, nowadays people want, $1 radio. $1 radio means, less than $1. They're not going to pay, more than $1 for radio. So nowadays, two chip or three chip are available. Two chip or three chip solutions are available. This different chip, baseband, IFN analog, and then RF transceiver parts, and implementing all the high Q pass on the package. And this can be system on chip plus embedded passive solutions, and then we can put some kind of filter solutions in the multi-layer filters, and also in the back side we can put some planar antenna here. There will be maybe some kind of coupling issues, but there are some solutions to resolve this. Because we can build some kind of a little bit directive antenna. Maybe it's gonna be okay. But if this is omnidirectional antenna, maybe it causes a lot of coupling issues. So that is a hot topic to solve, to do research. Okay. Development of RF SOP, the procedures. Initially, we need to define the scenario first. Okay, what kind of applications, what kind of scenario you have? Is it sensor network? Is it some kind of RF, wireless LAN applications? Depends on the scenario. You need to come up with some system level, architectures. And then this is some kind of a system level simulation tool. We use the ADS, tool. And then finally, based on this kind of system level simulations, we can come up with okay, these components can get this kind of spec, and we can define all the specification for each component. And then based on system simulations, okay, this system architecture can achieve the target signal level, SN ratio or ACPR ratio, and then we can come up with MMIC design, and then the other parts to build up some kind of package solutions. We come up with passive design, and finally we can achieve some module integrations. This is one example of this whole procedures. Okay, as I told you, I'd like to show just the two prototype demonstrations. First, focusing on the compact silicon-based power amplifier module. Here you can see some kind of landmark, so you can follow this one. Don't lose your focus. Okay, here is the introduction. Power amplifiers, as I told you, in RF transmitters, is really, really important. Especially, it consumes most of the power, a lot of power, in transmission mode. So, and also power amplifier operate in the nonlinear regime. Okay, so it affects the linearity a lot. And also, the cost-wise, it is almost 1/4 of that. So, if you are targeting $1 radio, your PA should be at least less than 25 cents. So, and also, in that point of view, a driving force for the PA area right now is the cost. There are cost reduction strategies available. One is silicon-based technology, and the other one is high levels of integrations. So there are some issues of CMOS PA. Transistor itself, there are some limitations. As I mentioned, low breakdown voltage, especially drain to source breakdown voltage, and then drain to gate breakdown voltage. Especially when you get high mismatch on the output side, your PA may burn. You see what I'm saying? If you don't have a margin for the breakdown voltage for the CDZ, drain to gate breakdown voltage, your PA may be distracted due to the reflected power. So this is very critical. At least people want 3 times larger breakdown voltage than the biasing voltage. If you are using 3 volt, at least you need 9 volt breakdown voltage for the drain to gate breakdown. And also drain to source breakdown is also important because it limits the power level of supply voltage. And then transistor itself has high knee voltage. That means what? You have a high knee voltage means if you have IV curve here, your current IV DC IV characteristic shows there are knees, isn't it? It turn-on voltage, such as turn-on voltage. This turn-on voltage has a lot of loss on the drain side. That means your drain resistance is very high. That means whenever you supply some voltage to the TL, you automatically lose some power level on the drain resistance. That results your poor efficiency. So those two issues are very, very critical to achieve high efficiency power amplifier. And the other issue is the passive components. As I mentioned, lossy silicon substrate. You have a lossy silicon substrate, so your RF signal easily can go through the substrate, and then you lose a lot of RF power, even though you have a good power generation is available from the device. But your interconnections lose a lot of power due to this kind of lossy substrate coupling from the RF trace to the substrate. So, and then the other issue is the thin metal layers. I mean, on conventional CMOS technology, the thickness metal is only 0.8 or 1 micron, and then dielectric metal is also dielectric also very thin, 1 micro or 2 micro. So your connection interconnection distance from the substrate is very, very close. So a lot of RF coupling in there. That's the reason why this lossy substrate affects a lot the RF performance. Yeah, there are 4 different kind of approaches we used. One is a CMOS PA integrated with chip passives. So everything is on chip passive. All the inductor implemented on chip solutions. And CMOS PA integrated with MEMS passives. And the other one is a CMOS PA integrated on package and input and output matching on LTCC. This is low temperature copper ceramic, sort of multi-chip module based on the ceramic process. And also finally, silicon domain HPT PA integrated on package solutions. This is one example for the inductor on-chip inductor, incorporating patterned ground sealed on-chip inductors. As you can see, the current flow is perpendicular to the ground trace. Using this kind of scheme, we can minimize the eddy current on the substrate. So that's the reason why this inductor can achieve more high Q values. For this kind of pattern ground, we can use polysilicon or M+ diffusion layer. Initially, we use a polysilicon, and we compare the result with the pattern ground inductor and without pattern ground inductor based on the polysilicon technology. We found that there's no difference. The Q of inductor with PG is lower than that of inductor without PG. And then finally, we concluded the inductor trace close to PG introduces additional capacitance parasitics. So this additional parasitic capacitance, degrades the inductor performance a lot. So we found the M+ diffusion layer is much better to implement, pattern ground. And then this explains us, much less parasitic capacitance is introduced by the M+ diffusion pattern ground. And we noticed, Q can be enhanced up to 20%, and also the effective inductance is not that much different. So based on this kind of technology, we developed 2.4 GHz integrated PA. This is not for targeting wireless LAN. This is for targeting, DAC applications. So we are targeting some kind of, high efficient power amplifier. So this is some simple circuit based on the, simulations. This is RF choke, and then capacitor coupling. This is, DC blocking, and also contribute the interstage matching. As frequency goes up, two impedance is very different. If two impedance, input and output impedance is too different, in that case, your signal reflected a lot, and then there are a lot of mismatches are available. So you cannot get, good transfer, from here to here. So impedance matching is a critical point. So this capacitor and this inductor acts as a, inner stage matching and also DC blocking performance.
Dr. Hugh?
Yes.
When you use the silicon, this is a high resisting silicon or just
No.
a regular silicon?
No, this is conventional regular silicon. We are using silicon on insulator also.
So then you have
Much better, Q factor of the passives, but the other issue is the thermal.
okay.
yeah, a lot of issue. Especially you are targeting high power amplifier, or if you are not considering PA, yeah, it's perfect.
Your inductor pattern looks like all square type of. Are there any circle?
Runtime, yeah.
Yeah. Which one is better?
I didn't prepare that slides, but we are using that.
Which one is better? The
Which one is
circular
better? Circular is better.
Circular is better.
Yeah. We can you can have analogy such as fluid flow. If you have edges, your flow is not smooth, isn't it? Yeah. Yes.
Is the circular better? Why are you using the square ones?
Some foundry is limited. Some foundry means mimic foundry doesn't support those kind of
Probably mostly
circular.
software capability.
Yeah.
Draw the square of straight line is much
Yeah.
easier than
Yeah.
rounded corner.
And software also, foundry and software also, yeah.
Because actually the 2.4 gigahertz, particularly in 802.11, then you go
11B?
5 gigahertz,
Yeah.
all this corner will radiate.
Yes, definitely. That's good point. Yeah, that's good point. It's and then the inductor value going to be minimized also is compared to 2.4 gigahertz because we can have some smaller turn. I mean, it's possible to use. This is 2.5 operations and 2.4 gigahertz. We can achieve 22 dBm output power, more than 20% efficiency. So it's even though we improve the passive elements, the efficiency itself is poor number. So commercially, it's available more than 30% or 40%. In the paper, they are claiming 50 or 60 something. But CMOS area still, the number is not quite clear. Some people say we achieved more than 50%, but their gain is poor.
And number on your SOI chip, silicon on insulator,
Yes.
are there any of those numbers?
Silicon on insulator cases, I haven't seen a lot of PA efforts recently, but they are developing Peregrine that has the silicon on insulator foundry. They are developing RF transceiver, especially for targeting 802.11b, not A. But currently, they are involving in the 802.11a also.
How will the design change from this wireless LAN to what is this?
Yeah,
What is the
topology-wise, not many difference. Topology-wise is similar, but the target is different. One is should be linearity. The other, this one is targeting for the efficiency. So there are two different way. Actually, nonlinear-wise, the optimal matching point is different. Okay, if you are targeting high linearity, your target matching point is different compared to high efficiency point. So
does the difference in bandwidth affect your design?
bandwidth also, yeah, definitely. And then you need to DQ. You need to some DQ circuit. This is already DQ circuit, so I think this is gonna be broad because lossy inductor, DQ the circuit, and then you may get more wideband. Okay. Okay, this is one other power control additional feature for the PA control. This is the gate voltage. So changing this kind of designing this kind of 2 to 4 decoder, you can choose. You can control the the input voltage here, and then finally this kind of switching nodes. You can change the impedance level over here, overall level. So and then the gate voltage can change from the VDD and then VDD minus 0.5, VDD minus 0.6. So you can change the gate voltage conditions. That means you change your drain current. Finally, you can come up with power control functions. So this kind of gate bias, the controller is assigned here, and then RF power and driver can be generate 12 dB, 16 dB, 20 dB, and 24 dB and different power level. And this is a micro machine, the solenoid inductor. We use this kind of a MEMS inductor based on the silicon wafer. This SU8 is negative PR, and using this SU8, we can stack up a lot of thick layer, and then finally we can control the thickness. That means we can separate the distance between the substrate to the trace, and make an opening here. We can use some electroplated process. We can control the thickness of the copper. Finally, to protect the oxidations, we can finishing with other material. So this kind of procedure, we can build up some kind of solenoid coil. This is applied to the power amplifier, to this kind of bias feeding line and the matching line, and also matching line. This is the actual circuit here. This doesn't show good number of the power performance. I'm sorry, but still there are a lot of room to improve the efficiency, because this is not self-tunable. So this is just promising solutions to get high-end silicon RF front end. This can be applied to the wireless LAN, and then any other topology.
Where is the moving part of this?
Which one?
Is the MEMS have a moving part?
This is MEMS?
Yeah.
Yeah, this is MEMS.
Yeah. So I'm asking, where is the moving part in this MEMS? Does it have any moving part?
No, no moving part.
So technically, what is the definition of MEMS?
What is the micro?
Yeah. How would you define a MEMS as opposed to a traditional RFIC?
Yeah, MEMS should be post process, and based on the post process, we can get thick metal, and then we can achieve high Q inductor.
Yes,
Using
sir.
just not only conventional process. Conventional gives us only 1 micrometer thick copper, the aluminum, but these cases we can use copper to have thick metal.
Yeah, I think I'm still confused. What is the definition of MEMS inductor?
Based on the MEMS technology, you build an inductor.
Basically, this is not exactly MEMS, just they use MEMS fabrication technology
fabrication.
to realize the three-dimensional
So
structure.
it's basically a 3D
Itself is
structure.
not a MEMS. Yeah, it's a 3D structure, not a MEMS.
Because it doesn't meet my definition.
I see, I'm sorry. MEMS inductor means just inductor based on MEMS step technique.
Yeah, use the MEMS fabrication procedure.
So
What's how many nanohenry you can get? Use this one.
This one is less than 3 nanohenry.
Then what's the advantage you compare with previous one you?
On chip,
Yeah, on
and we
chip.
can achieve more high Q.
This one more high Q just because you don't
Right.
have imaging current in the silicon top.
And in addition to that, you can minimize the loss of the inductor trace. Because the metal length, metal thickness also.
Okay, metal thickness in this case you can use much thicker metal.
Sure, up to
Okay.
12 micron.
Enhance your
Yeah.
conductivity.
The conventional RF CMOS technology, we can get currently 4 micrometer thick, pretty thick, but still, if you can use this kind of technology, we can achieve more high Q inductor.
Actually,
Yes.
if you use the planar structure and optimize the thickness of your metal layer, it's possible to achieve very high.
The issue is
The key problem maybe is still the substrate is too
that's
hot.
if you are using SOI, it's okay.
Yeah, then it should
Yes,
be okay.
definitely. On the gas IC cases, there is no problem.
Yeah.
We can easily achieve 12,
Semi-silicon.
yes, 12 to 20 Q factor is achievable. If you are using semi-insulating gas substrate or silicon on insulator such as SOI technology, it's possible.
3D structure, if can move it, then it's nice. You really can start to tune it.
Yeah,
Otherwise,
there
a lot of
are
problems.
another funding resources from DARPA, isn't it? That is intelligent RF front end. Have you heard about that? That is incorporating tunability on the RF circuit. as I mentioned, initially, it's really hard to achieve, one-time success. So they'd like to implement some kind of, tunability of the RF circuits.
Possible is separate this inductor into two pieces.
Yes.
And use the static charge and moving the distance between two parts, maybe.
Yes.
Yeah.
And also some, tunable capacitor.
Yeah.
Yeah. Tunable capacitor.
Capacitive.
Yes, yes,
tunable.
yes. Using MEMS technology, we can, change the distance of, the capacitor and then.
So, you say this is higher Q. What numbers for Q can you achieve with this, and what with the planar?
The planar cases you can achieve, 3 or 4 on chip. This can be, 10, 15.
The planar problem because it's built on the silicon. Then you have current like this. Silicon is not to insulate. If it's glass, then have no imaging current.
It's okay.
Otherwise, the top current go this way, the bottom current go this way, and generate a heating and a loss.
Yeah, people
So
call this
the
eddy
Q is
current.
not high.
Yeah.
However, if you use the SOI, SOS, silicon or insulated silicon or sapphire, or just the build on the glass, then it should be better, much better.
Yeah.
For reporting,
Just,
better.
you are considering just a transceiver, except power. It's much better to use SOI technology. But if you have to consider, PA, it's a little bit different. So. Okay, this is just the unpackaged inductors. Similar, story. We have a different kind of, inductor. We can control the distance here, and then we can control the overlapping, area. We, control the distance here and also overlapping here. So after, testing this kind of structures, we found, this 3D helical gives us the best, performance because maximize the distance and also minimize the overlapping of the area. This is one kind of, packaging inductors. This is not the, on-chip inductors. This is a packaging inductor. Using this kind of packaging inductor, we can achieve more high Q filters and also duplexer. And finally, we can get, some reasonable, antenna. This is the inductor Q. As you can see, much higher number, 100, compared to 10 or 20. Yes, speak frankly, high Q number doesn't mean high performance RFIC, because as Q number is goes above a certain number, it doesn't affect the improvement anyway. You see what I'm saying? If at least you have 30 or 40 Q factors, it's okay to use. That means if you have a Q factor of the resonator, let's assume 30, and then you have resonator Q 120 for the VCO, the phase noise doesn't change a lot. So people keep saying we got this number of Q factor, we got some Q factor, we have 1,000. It doesn't mean a lot, especially for the VCO design. But maybe for the PA design, definitely a little bit slight impact. But anyway, we can get high Q factors based on this kind of packaging solutions. And this is another story. This is for the capacitor. This is MIM capacitor. Those two metal layers are built up to the dielectric layer. This is maybe 4 mil or 8 mil. And then this is another topology, vertically interdigitated capacitor, giving us a similar capacitance values. So using this kind of topology, we can get more high Q number. I mean comparable Q number and SRF and to the MM topology, but we can minimize the lateral real estate. So we can get this vertical interdigitated capacitors, and especially for the RF shorting for the bias line. Let's assume you are designing 5 GHz RF line, and then you may need at least 5 picoheli or whatever. That means if the total area is pretty big. So, and then you are using some kind of interdigitated vertically interdigitated topology, you may minimize the lateral size of the inductor, the capacitor. The Q factor, 200, and the capacitance value is 2 pico and 1 pico. Yeah, those kind of numbers.
What's the reason when the operating frequency go to higher, your capacitance even go to higher when beyond the 4 gigahertz?
You mean this one?
Yeah.
Q factor is degrading a lot.
Yeah. That's understood.
Mhm.
And why the capacitance value is increased quite a lot?
Actually, a lot of plastic is involved. It's not make a constant value. So whenever you look at the real response of the capacitor, a lot of plastic is combined together, and then the capacitance value is not maintained
That's true.
as the same value. So finally curled into the a little bit off from the normal
Those are measurement value or those are
that's the measurement
simulation value?
measurement.
So probably just a parasitic
Yes.
pickup,
Yes.
instead of the intrinsic capacitance.
Intrinsic capacitor also plastic, isn't it?
Mhm.
Not only pad, but also intrinsic. Okay, this is a 1.9 GHz CMOS LTCC PA, just to show the brief idea. This is implemented on chip, and then the other parts implemented on the LTCC parts. This is the way just demonstrate the RFIC, and then demonstrate the feasibility of this kind of technology to implement RF components. This is one example, 1.9 GHz, and CMOS technology. This is an on-chip inductor and on-chip capacitor, and the other part is implemented on the package. And this is the other example, 1.9 GHz fully integrated CMOS LTCC PA. These two chip is implemented just on chip, and then the other parts is implemented on the package. So you can achieve more than 40% efficiency, and then gain is 15 dB, and the power level is almost 24, more than 24 dB.
In these kind of designs, how do you convert the circuit into the implementation? Do you have any systematic?
Yes, because initially, based on the EM simulator, that is IE3D, from GLAN software, GELAN software, and then we can simulate everything. And then from that point, using the some kind of modulus tool, we can convert to the circuit, equivalent circuit. And those equivalent circuit can be implemented in the circuit simulator, such as ADS or cadence tool. And then you can incorporate those kind of model, and then those kind of model together, you can simulate the power amplifier over performance.
You have an analysis tool, but there's no synthesis. Is there any synthesis capability?
No, we are not using synthesis.
You have to guess what type of structure.
We need to extract the model. We need to build up the model, because this is a RF area. Yeah.
So these are done with experience. You figure out how much of a turn you need, and
Yeah, definitely. This is one type of approach. I'm not saying this is the best solutions. This is totally depends on the applications, and as I mentioned before, okay, this part up to this part we can implement on chip, and then the other part should be on package. So totally depends on the application. Totally depends on the frequency. Yeah. So if the sensor network, just focusing everything on chip, it's possible based on the silicon technology, or silicon on insulator technology, or silicon germanium technology. Everything is on chip is possible, including mixer, LNA, VCO, okay, and some filter, image rejection filter. Maybe antenna may be questionable, but it's possible to implement everything on chip. And for receiver part, we can implement, direct down receiver, and also we can implement direct down, direct up transmitter. This is the other, 2.4 GHz CMOS LTCC. Power MOSFET devices size is 3 millimeter overall, width, and then 23 dBm and 45 power added efficiency at 2.4 GHz. The operating voltage is 2.5, and we used some kind of mesh ground for the grounding. Actually, we cannot cover all the backplane with a solid ground because there are some process limitations, bending, those kind of process issues. So we just use the mesh ground. This mesh ground cases, should meet this kind of criteria. The length of this distance should be less than lambda, over 10. Okay, the silicon germanium HPT power. I'm talking about too much about the PA, but this is one example. Okay, and power amplifier in silicon-based technologies. Silicon germanium HPT is, we are using silicon germanium HPT to use the HPT devices. There are a lot of HPT devices advantage in the silicon. Especially, we can achieve, high efficient, power amplifier. Also, keep saying, we can achieve more linearity if you are using HPT technology. There are some kind of analysis based on the some simulator such as Volterra series analysis. But there are a lot of interesting research is ongoing right now to improve the linearity of the HPT based on the focusing on the device issues, focusing on the design issues, and also. We can enhance the native device performance, incorporating class F like loading. That means on the output side, we can put some kind of matching circuit, control the waveform of the output signal. Voltage signal need to square to achieve high efficiency. So using this kind of harmonic tuning circuit, we can achieve high efficiency values, and harmonic suppression filters can be used for improving the to suppress the harmonics, second and third harmonics. What is class F operations? The loading impedance, the second harmonic should be shorted, and then open at third harmonics, so we can make squared wave of the voltage. And then the performance-wise, we can achieve more than additional power, 0.6 dB additional power compared to class B, and then no power dissipation at harmonics. So we short it out and then reflected the third harmonic. Ideally, we can achieve 99% efficiency, but practically we can achieve more than 60% efficiency. In that point of view, we need a compact implementation of a load network. Okay. This is 2.4 GHz silicon germanium HPT power amplifier. This is bias network. This bias network should be very carefully designed, especially desensitize the bias circuit with versus temperature and versus bias supply voltage, and also process variations. I'm not sure how many people involved in the circuit design, but whenever you design some circuit based on the silicon technology, you may get a lot of different model, slow, typical, and fast model of the MOSFET. That means, depends on the process, a lot of variations in there. Even March process different compared to last January process. So sometimes the process gives you good device, but sometimes a little bit poor devices. But your circuit is very sensitive to those kind of process variations. Your production of the components is going to be in trouble, I think. So this bias circuit is very insensitive to those kind of variation of the process. We use the IBM silicon germanium 5HP process. Currently, we are using IBM 7HP and 8HP. The FT of the 8HP is almost goes up to the 200 gigahertz. It's amazing. That means we can use up to 20 gigahertz design. And the high breakdown device is also possible based on the IBM 5HP devices. And we packaged 8-pin mini SOIC packaging. There are important issues for the HPT design. That is a balanced resistor design. balanced means, if you are combining a lot of, HPT cell, your base emitter junction is may have different voltage drop, and then all the current flowing through some certain area. That means your channel temperature goes up. Finally, you may come up with some kind of collector current collapse. So this is very important to put some ballast resistor to desensitize those kind of difference of the base to emitter voltage variance. This kind of collector equation can be expressed like this kind of mathematical expressions. I'm not sure you are quite okay.
The math is more comfortable. I know what that is.
I'm sorry about that. Anyway, this is ambient temperature and thermal resistance. Thermal resistance represents, if you are consuming certain power level, how much, your channel temperatures goes up. Okay? If you are assuming 1 milliwatt, and then your temperature goes up 0.81 Celsius more. Okay? So this is thermal resistance. And then this is power consumption, DC power consumptions. And due to the DC power consumption multiplied by RTH gives you some certain degree of temperature increase due to DC power consumptions. And your ambient temperature, room temperature, or you are in summer or cold weather like this, it's pretty cold here. In Atlanta, it's much warmer than this. But your circuit operating here in Atlanta may be different.
So is it better here?
Yeah,
It's better, right?
Ideally, it should be better. Okay, so yeah, this is better. Place. So ambient temperature 125 Celsius. This is maximum, criteria, and then band gap is, represented by that. I mean, the 1.21 electron volt, and then beta. Beta means, current gain is also depends on the temperature. Based on this kind of information, we can plot the, the current density versus, base emitter voltage. And you may come up with, if you are not using any emitter ballast resistor, your current flying back, that means, unstable. It represents, if you are applying certain value of, base emitter voltage above certain value, like this, and then your TR doesn't give you, what you are expecting. That means that there will be some kind of, emitter crowding effect or current collapse effect. Okay, you are expecting this much current, but due to this kind of effect, you cannot get this kind of current level. That current level is collapsed. So, if you put some kind of resistance value here, like 1 volt, 1 ohm, 2 ohm, 3 ohm, you can get more stable response. So emitter ballast resistor or base ballast resistor is pretty important, especially for the HPT design or BJT design. So we picked 3 ohm per transistor. Here, emitter ballast resistor cases, you can put some kind of resistor here, but the disadvantage of this one is you lose some kind of voltage swing here, and then gain. As you can see, this is a negative feedback area, isn't it? So this negative feedback, minimize the voltage swing here. Your overall, there will be some kind of loss of voltage swing. And the other choice is you can put the ballast resistor to the base side. This base resistance should be larger than emitter ballast resistor, at least beta times larger, because your current level is beta times larger. And then there are still lots of RF power in base ballasting resistance, because we are using at least 1 ohm resistance overall. But this itself is much larger than this one. Let's assume the beta is 100. This should be at least 100 ohm. But this is connected parallelly. Let's assume you're combining 100 cell. The total resistance overall equivalently is 1 ohm. So this is 1 ohm. So solution, we can remove the base ballast resistance from the RF path. So this is the suggested, novel base ballast resistor scheme. we can put the base ballast resistor on the DC path only. There are no base ballast resistor through the RF path. This is RF path, RF signal path. This is DC path. So we just need to put the base ballast resistor on the DC feeding path, so we can overcome those kind of issues. This is biasing explanation for the silicon germanium HPT PAs. The current can be expressed, base current can be expressed like the discrete equations: saturation current, base voltage, and then VT, and then beta times larger than IC current. And then DC currents on the RF drive can be expressed this way. This is RF drive, and this can be decomposited, two different kind of DC area. I mean, these components can be expressed like using modified Bessel function of the first kind of order 0. As you can see here, traditional biasing scheme, if you are using constant current bias conditions, that means your IC is fixed. Your base voltage falls at increased RF power. Your RF power increased, your base voltage should be decreased to maintaining the constant current of the collector side. And the other issue, if you are using constant voltage bias, your IC increases with RF power increases, because RF power is proportional to the these Bessel functions. So this is the suggested novel biasing scheme. This is the targeting the amplifier, and then this is the replica of the TR. Let's assume this is 100 cell. Maybe this guy is just one cell. We have to use the same cell but different number of fingers, and first we need to implement bandgap reference currents using output circuit, outside circuit, external circuit. We need to have a good bandgap reference current. Changing the ratio of those two numbers, we can pick M1 using ratio, number of the ratio. We can get the n times larger current to the collector side of X1, and then picking this resistance, and then changing those M3 and M4, we can finally come up with n times larger I base current compared to this guy. You see, the resistance value is n times smaller than this one. And finally, the collector side of the target bias, target device, you can get n times I reference current. As you can see, all the current is just based on the ratio of the device. That means it is desensitive to the process variations. Even though there are process variations, this current is just defined by the ratio of the device size. So we can overcome those kind of process variation, and also you can overcome the temperature variation, such as GM and then VT has a strong temperature variations, isn't it? So in that point of view, if you are using just a ratio, you can minimize those kind of dependence of the process variation and temperature variations. This is a summary of the, and then there are some simulation results of biasing network. As you can see, if you are changing the temperature here, the output collector current variance, such as less than 1% change of temperature, and here temperature versus output stage collector current. We change the test model and then typical model and slum model. We can see less than 1.5% change versus the process variations. The LTCC output network, we implemented some kind of filter. We used multi-layer ceramic substrate, high Q, and vertical integrations, and used Kyocera 10 middle layer process. For the output network, to make short stub, we use the quarter wave length, even harmonic short circuit, and also harmonic suppression filters. Using harmonic suppression filter, we could minimize the spurs and third harmonic, and we use some single step for matching, and then that means second and third harmonic cases, fundamental cases almost 50 matched, and then second harmonic is almost short, and third harmonic is almost open. using that kind of harmonic combinations, we can make the voltage square wave. That means we can get higher efficiency. So finally, we build up those kind of silicon germanium RFPA. This is a third stage and second stage, and then all the bias circuit here, and then capacitor bank for tunability, and then first stage here, and all the components should be downbonded to make a robust ground. Whenever you see the simulation regime, whenever you simulate the third stage PA, the voltage swing is totally depends on the power level. But this kind of cases, as you can see at least 8 volt max or 12 volt max. If you don't have a robust ground here, you can see a lot of ground bouncing. Your ground bouncing deteriorate your power added efficiency a lot. So you need a lot of wire bond to make a robust RF ground. This is very important as your frequency goes up. This is the performance summary, and we can achieve 27 dBm output power at 0 dBm input. 27 dBm means half watt, okay, and 45 power added efficiency, and 35 dB linear gain. And then all the harmonics, response is less than minus 40 dBc compared to the carrier. This is the summary. We demonstrated silicon-based PA amplifiers with different level of integration towards RF SOP. First, integrate on chip with chip passives and with the MEMS passives, and also integrate on package and fully integrate on package solutions. Just this kind of approach can be applied to RF transceivers based on different kind of applications. So we can pick which one we have to go. We can pick based on our simulation and our scenario for our applications. Next topic is next prototype demonstration is compact RFIC module for 802.11a wireless LAN applications. This is based on the GaAs technology, but nowadays the silicon technology is also available. We developed 802.11b, 802.11a RF transceiver based on the silicon germanium technology, and then 802.11b, that means 2.4 GHz direct down receiver also available based on the CMOS technology. But this is GaAs technology. I'm not sure how many people are involved in the GaAs area, but this is one example. Yeah. Motivation is there are a lot of demands for higher data rate. So broadband transmissions. So at least 2.4 GHz and then 5.8 GHz. So we can get more higher data rates performance. And there are significant RF interference, especially around 2.4 GHz, such as a microwave, a lot of issues in there. And also 802.11a, in that point of view, 802.11a is more attractive for their high data rates in densely populated area. But this is short coverage, isn't it? And then more access point is necessary. So we need low cost solutions and compact solutions. A lot of people want those kind of low cost, low power, and compact solutions. Okay, this is the summary of B 2.4 GHz. Those topics you guys knows better than me. I think 802.11b 2.4 GHz and direct sequence spread spectrum they're using, and up to 11 megabps data rate, and the range is almost 200 and 300 feet, and there are some significant RF interference. 802.11g is OFDM method and more than 20 megabps data rates, and also 802.11a they're using OFDM and also high throughput up to 54 megabps, and short range less than 150 feet. And in that point of view, we need more access points, so and densely populated requirements. The system architecture based on system simulations, we picked okay, this is the reasonable technology we can use. But nowadays we cannot say that. At that time we said okay, this is the best solutions to achieve this performance. finally we decided, GaAs MOSFET to achieve, 5.8 gigahertz transceiver. And this is single chip integration, LNA-PA switch. And also here we can implement mixer and VCO. It's okay. There is no problem to implement that. And also VCO plus, PLL, isn't it? So I mean PLL. So here just to show the feasibility of the some kind of SOP solutions combining SOC of GaAs technology. We picked 0.6 micro GaAs MOSFET, and we choose the LTCC bandpass filter based on the Deuk Hyoun 943 tape. And this LTCC bandpass filter consists of embedded folded coupled line structures to filtering out the image reject. This is LNA design. Based on the simulations, we can pick the optimum device size. We cannot use just a small device size. We cannot use the large device size to implement LNA. Okay, you need to optimize the device size. Okay, based on the analysis. Okay, this is the optimum device size to achieve high linearity and then high good noise figures. So based on those kind of simulations, we found 300 micrometer gate width is the best solutions. And also we picked the cascade structures. This gives us good isolation from the input and output. Based on this kind of cascade structures, if you are changing the output impedance here, it doesn't affect a lot to here, because cascade structure gives us a good isolations. So if you need to change some impedance here, there is no need to retune the input circuit. So in that point of view, this cascade structure is pretty good. And also there are some current reuse technology. There is no need to supply this one and this one separately. This is one path of the biasing scheme. So if you apply some bias here, this current used at this point also and here also. So we are saying this is current reuse technology. Based on this technology, we can achieve noise figure 2 to 2.4 dB, and then input total the intercept point is 8 dBm, and 3 volt applications, 3 volt of power supply, and 13.2 milliamp power current consumptions. And this inductor is very important. This is inductor degeneration scheme. If you are not using this kind of scheme, your optimum matching point for noise and your optimum matching point, for the input VSWR is quite different. That means if you are targeting good noise figure, you lose the input VSWR. That means you are quite off from the 50 ohm. But you are targeting just 50 ohm matching, you cannot achieve good noise figure. So using this kind of technique, you can make it closer. The 50 ohm matching conditions and then noise figure matching conditions closer and closer, and you can pick in the middle of the matching point to achieve good noise figure and then good input this one. So people say this one is a inductive degeneration matching technique. This is a PA design, and this is two-stage Class A operations because the targeting is different. This is not the high efficiency PA. This is targeting the linear PA. So we picked the Class A operations. To get more linear operations, you can incorporate some kind of a pre-distortion circuit also. But here, two-stage Class A operations, and also you can pick the size correctly to achieve the required power level. The first device size is 1.5 and the second is 2.4. Initially, this is pretty bigger than actually requires. But to give us some kind of margin to push the power level of here, we picked a little bit larger device than expected. So this is an oversized device at that time. And then this is some kind of simulation method, dynamic load line method in the ADS or MDS environment. You can see the dynamical load line behavior on the simulation environment. So based on this kind of technique, you can build some PA. This is inner stage matching, and then RF choke here, and then output matching. So operating frequency is 5.12, 5.8 gigahertz, and power gain is almost 15 dB, and output P1 dB is 24 dBm, and output OIP3 is 41 dBm, and IM3 at P1 dB conditions larger than 25 dBc, and harmonics at P1 dB is 28 dBc. Overall, input visual is 1.5 to 1. And this is switch design and single pole double throw configurations. We pick DFET because DFET has a higher P1 dB, and this device is optimized for the insertion loss and isolations. We picked the device size for the series. We picked 1.2 millimeter, and then for the shunt, we picked 0.6 millimeter. This gives you more additional isolations between those two paths. Whenever this turns off, this turns on, this path should be has good isolations. That's the reason why we added up more additional shunt MOSFET to gives you more good isolations. The insertion loss is 1.2 to 1.5 dB, and isolation is 2420, and return loss is 13 dB. The input P1 dB is larger than 28 dBm for TX mode, and then RX mode case is 26.5 dB. And this is the filter configurations. We use multi-layer version of a conventional filter. The tool to build up this kind of filter based on the EM simulations and IA3D, and embedded folded edge coupled stripe, and also 3 ground plane is connected all together to have a robust ground, and streamline to CPW transition was used to build up the filter line. This is filter itself, the port of the filter, and then only for testable using coplanar probe pad. And this is 20 layer, and dielectric constant is 7.5. The thickness of each layer is 4.4 mils. And then insertion loss is 3.5 dB at 5.8 gigahertz, and then return loss is 15 dB, and immediate rejection is 22 dB at 5 gigahertz. This is the LTCC overall, front-end module, and then PA and LNA and switch. And this is the overall, module, including the bandpass filter in front of the antenna. So RX and TX measurement result is, overall gain for the RX chain, 11 dB at 5.8 gigahertz, and immediate rejections, we can achieve 27 dBc. IIP3 is 7 dBm. And TX chain cases overall gain is 11 dB at 5.8 gigahertz, immediate rejection is 20 dBc, and then output P1 dB is 20 dB. Okay, this is the conclusion. We demonstrated highly integrated broadband, high linear front-end, single gas MOSFET MMIC, and then we used the embedded 3D LTCC-based bandpass filter, and we demonstrated the feasibility of on-package integration of RF front-end system based on the system-on-chip solutions. You can design system-on-chip based on the your applications, and then you can integrate using those kind of packaging solutions. You can integrate antenna and all the high Q passive solutions to this SoC solutions to achieve high-end RF transceiver. Okay, this is the procedures. First, you need to define the system. Yeah, you need to come up with some scenario, and then based on system simulations, you need to define the spec, which components require what kind of specification, and need to define the system partitioning. Okay, this should be implemented in the system-on-chip solutions. Okay, which kind of technology? And then you need to design, active design, all the active circuit, and then based on that, you need to do some thermal analysis also, especially including those parts. The layout optimization is very important to minimize the overall size, and then decouple all the interference between the design to design, digital to analog, analog to RF. And then packaging solution, we can pick material, which material is best for low cost or complex solutions. you need to do some kind of EM simulations to get accurate simulation result. And also you need to develop off-chip passive design, and also you need thermal design. Okay. This is my research directions. This is a local area network and then metropolitan area network. Right now, I'm in here. Okay. So this is wireless LAN applications, and then 1394, IEEE 1394, and also wireless 1394 is here. Right now, main focus was here, but I need to broaden my research area to high mobile, RF transceiver, and also some kind of optoelectronic transceiver also, because this is a very hot topic for the backbone nowadays. And then 2.5 and 10G and 40G, and actually I have a strong interest also work with some sensor network around here. Yeah. So this is the research directions. Can be a diagonal this way, but currently I'm here, and then I'd like to plan to move a little bit here and then here, and also including this kind of sensing network. This is my dream and my vision. Next generation communicator. It has all the standards: GSM, YCDMA, and 802.11bg, and 802.11a, and then 4G cellular, wireless, IEEE 1394, and Bluetooth, and next generation LAN, especially for targeting 60 gigahertz.
A single chip.
That's my vision and dream. Currently, I'm here, just achieving each of them. Yeah. And then,
is that dream, do you think, ever going to happen? I mean, in a sense that
we
as
can-
soon as you can achieve it,
Yeah,
can you
if-
build something cheaper that just
cheaper,
does
yeah,
that?
yeah. If can be cheaper, definitely
Or
we can do.
uses less power, or
Yeah. But it can be separated certain parts, but this is ideal. Whenever you have just the one terminal and you can access everything.
It's funny because the message I took away from your talk to sort of a layperson like myself is that given a particular application, right, of a set of frequencies, a certain transmit power,
Yeah.
you find that specific kinds of technologies or design choices are the best, right? And it seems as though the message of the last hour is that to do this all in one physical layer somehow is you'll always give up something.
Yeah.
Right? A smart
Yeah.
guy like you will always be able to design.
As I told you, this is
solution.
dream. As I told you, this is dream. If I can achieve, this one is the best, I think. You see, but
Maybe it's just a nightmare.
to be realistic, maybe we can come up with 2 or 3 available technology. We have to pick it.
Well, it could have some application to a universal base station or access point.
Yeah.
Which has IP behind it. Just plug it in and it will figure out what protocol and what radio.
And some people always said the software radio is going to do this.
Yeah, software radio is
But
one.
it seems like you're
target.
saying it's the hardware radio is the
What kind of software radio?
Some combination of it. Anyway, software radio also requires
If it's
hardware.
all in one. Okay,
I'm sorry.
very- no,
Just
it's very
I'm saying,
interesting.
just
No, I'm just-
just
I
as
understand.
I told you, yeah. And future work and the research fund, source, I'm gonna summarize a little bit. I'm targeting NSF fund and then some DARPA fund. Definitely, I'd like to, get the new faculty career work. I know it's not easy, very tough, but if I couldn't get it, maybe my advisor gonna be angry about that. So I need to move, very hard, and then to get this one, and also the DARPA the other, NSF, some kind of collaboration with the WINLAB, sensor and sensor network. This is not correct anyway. A little bit, low cost and low power RFIC for wireless sensor network. This is a little bit different, scenario. And DARPA MTO, wide bandgap semiconductor technology, using this kind of program, maybe we can achieve a more high power microwave circuit targeting base station, That can be one solution. And also, as I mentioned, DARPA program, MTO, Intelligent RF Front-End. The program manager is Edgar Martinez. I haven't met him, but I'd like to be introduced by my advisor to meet him and then talk about smart RF module. So this is one target for source. And finally, DARPA VLSI photonics and radio frequency light wave integrated circuit to targeting radium fiber. Yeah. And the other funding source from industry, I work for National, I work for LG. Currently, I'm writing proposal for Cree microwave, developing some kind of LTCC power amplifier to achieve a high power amplifier. I'm currently writing the proposal to Cree, and this is a short-term project. Even though this is 6-month project, very short-term, but the amount of money is not small. I think it's attractive. So, and this one, and also Samsung currently started new program with us, and also I came from South Korea, not North Korea, and I have I can make some strong relationship with some companies, Samsung and LG and Hyundai. And Samsung especially has a strong interest in developing silicon germanium technology and CMOS RF transceiver for cellular applications.
What do you mean smart RFIC?
Yes, smart RFIC module is reconfigurable. Configurable. Sometimes different bands, sometimes different modulation. Those kind
What's
of stuff.
your approach? Can you talk a little bit?
I need to think a little bit more. I haven't, get the idea right now. Just I'm thinking, some additional feature based on the digital logic, to achieve, those kind of smart RFIC. Based on the digital logic, you can control the, RF circuit itself.
Is there sort of if you I realize that your thoughts are preliminary, but are there constraints on the time scale of reconfiguration in a system like that? Like when you say, oh, it's configurable, does that mean you can reconfigure very quickly because it's hardware, or because it's hardware, it's very slow? Is that a dopey question, maybe?
Well, the maybe knows better than me, I think, especially with time-wise, the transition time-wise.
Well, I know traditionally what applications need, but I don't know whether physical hardware would make reconfiguration very fast.
There are a lot of dual mode PA, dual mode cellular, those kind of reconfigurable terminal, isn't it? So like that, if you're not just not right now, those kind of dual band, multi-band application, those kind of hardware is very, very bulky right now. The implementation is very bulky, and they are using a lot of replica of the similar. Yeah, so if you have more on-chip solutions, and then easy controlling of the RF parts maybe, and then you can get a little bit smart RFIC module for meeting those kind of different kind of modulation, different kind of band. So yeah.
We should thank our speaker.
Yes.
Thank our speaker.
Yeah. This is it. Thank you for your attention.